Okay. All right. Um, so welcome to the third week sample problem live session for digital signal processing. So we'll be discussing some sample problems which are more or less related to the assignment questions from the contents of week 3. And a quick introduction about myself. So my name is Avik Mukhopadhyay and I am, as you know, one of the TA for this course. So we'll try to discuss nearly 6 to 7 problems for today if time permits, and maybe if not possible, we won't be explicitly working out all the problems line by line, but the main point is that this session is actually supposed to be an interactive session. So it's not just me dictating the steps and working out the problems one by one. So I request everyone to participate, to interact during the session, think about how to approach the problem and respond. So with that in mind, so let's start our session for today. It's already 6. Okay. So yeah. Okay. So can you see the first and second question?
Yes, sir.
Okay, good. All right, so let's start. Okay. Okay. So remember that in week 3 the contents that were covered consisted of mainly the LTI systems, then the notion of convolution was introduced, and then we looked into a very important aspect of LTI systems, namely the impulse response, which plays a very central role in the LTI systems theory. Then we discussed some of the properties of convolution and checked whether those properties are valid everywhere in all cases or not, or are there any constraints that need to be met. And then we looked into the systems that are governed by LCCDE. So LCCDE stands for linear constant coefficient differential equation in case of continuous time systems, and it is linear constant coefficient difference equation in case of discrete time systems. And finally we saw the differences between FIR systems and IIR systems, so finite impulse response and infinite impulse response. So based on more or less these concepts, we will be discussing some sample problems. So let's start with the first one. Okay, so in this question we have been given a signal h of n equals to half to the power n minus 1 times the difference between these two unit step functions. So u of n plus 3 minus u of n minus 10, and we need to find the values of capital A and capital B in terms of n. We need to express A and B in terms of n such that the following equation holds. What's the equation? It says h of n minus k. So h of n is shifted by k samples, and it takes two forms. So in the first case, it takes the value half raised to the power n minus k minus 1, whenever k lies in the interval a to b and it is 0 elsewhere. So with these information given, we need to express a and b in terms of n. So it's a very basic problem. It's really just basic mathematics, nothing big deal. So we'll start with a very simple problem. So well, what do you think about this problem? How should we start? Yes, any guess? Okay, are people there in the call? Okay. Yeah, so I mean, yeah, just interact in the session. It's nothing really. So let me just write it down, note it down. So the first question is okay, so h of n has been given as, and please feel free to interrupt me whenever you have any queries or anything which is not clear, okay? And I'm also here to learn from all of you. So this is the given signal, and we have been given this another form, right? H of n minus k, which is of this form, half to the power n minus k minus 1 whenever k lies between a and b and it is 0 elsewhere. Okay. Yeah. So in order to, we need to find this a, what is a and what is b in terms of n. So you see, if we can relate this h of n and h of n minus k, both are exactly the same thing, just there is a time shift, right, by k samples. So if we can see the difference between the two, if you observe it, the first form, which is h of n, is just a function, single function, it's expressed in this form. In the second one, we have h of n minus k, which take two types of forms depending on the interval in which k lies. So if we can somehow match these two forms together, then we are essentially done. We can find the values of a and b in terms of n. So is there any way we can do that? So can you think of expressing h of n in a form similar to that of h of n minus k? So I already gave you a hint. So how do we go about that? Any guess? Yes. So there is nothing to worry about your response. This is nothing very serious. Okay, so please interact. These sessions are actually meant to be an interactive session. Okay. So anyway, so if you see this h of n minus k, oops, yeah, this takes two types of forms, okay? Whereas if we can somehow express h of n, what I was saying, in a similar form, then we can actually compare the two equations and then come up with the expression for a and b. So what about this thing? Okay, so this let me just change the color, and so if I ask you about working or not? Doesn't seem to work. Is it working? Okay. I think there's a huge lag. So yeah, you can hear me, right? Yes. Hello. Hello. Is the recording? Yeah, recording is in progress. So anyways, so we'll continue. So this, the highlighted function, this u of n plus 3 minus u of n minus 10, the difference between two shifted unit impulse unit step functions, what possible values can it take? So if we just analyze, so go back to this. So this function, it takes the value, it can, if you observe carefully, it can take only two values, either 0 or 1. So it takes the value 1 when n lies between minus 3 and 9, and it is 0 elsewhere. Okay. So clearly, if you can just verify it. If n is within, if let's say n is outside this interval minus 3 to 9, let's say n is 10. In that case, both these individual step functions will take the value 1, and the difference between the two is 0. So it will vanish. And whereas if n is less than minus 3, which is, let's say, n equals to minus 4, again both of them takes the value 0. So 0 minus 0 again is 0. Only when n lies within this interval minus 3 to 9, then the first function, which is u of n plus 3, it takes the value 1, whereas the second function, which is u of n minus 10, it takes the value 0, and we have the difference as 1 minus 0, which is equals to 1. I hope it is clear. It should be simple. So based on this observation, we can actually express our h of n in this form. So this difference becomes 1 whenever n lies between minus 3 to 9, and it vanishes. It vanishes whenever n is outside this, so elsewhere. Okay. So okay, now this condition, by the way, here, this was already, this condition here, it was given to us. Now we obtained this bottommost equation. Yes. Okay, I think you lost the connection in between.
Yes, sir. Actually, I was on my way from my school.
Ah,
So, yeah.
okay, okay. No worries, no worries.
Yeah.
So, anyways, yeah. So I was discussing the first problem only.
Okay.
So, like I was saying, this h of n was given to us. It was expressed in this form: half raised to the power n minus 1 times difference between two shifted unit step functions, right? U of n plus 3 minus u of n minus 10. And another function was also given to us, which is h of n minus k, and it takes two forms: half raised to the power n minus k minus 1 whenever k lies between a and b, and it is 0 otherwise. It was given. Now we need to find, we need to express a and b, these parameters capital A and capital B, in terms of n such that the condition holds. So, like I was saying that the forms of these two functions h of n and h of n minus k, if we can relate the forms, if we can match the two forms, express h of n in a similar form to that of h of n minus k, then we are done almost. Then we can simply compare the two equations again and come up with the values of a and b. So the observation to make here is that this difference between the unit step function circled within this red dashed line, so u of n plus 3 minus u of n minus 10, this difference can take either two values, 1 or 0. So it takes the value 1 whenever n lies between minus 3 and 9, and it is 0 elsewhere. You can just verify it. If let's say n is outside this interval minus 3 to 9, let's say n is greater than 9, let's say n equals to 10, what happens in that case? In that case, the first function, which is u of n plus 3, if you put n equals to 10 there, so it becomes u of 13, and by definition it is 1. For the second function, again, if you put n equals to 10, u of n minus 10 is u of 10 minus 10, which is u of 0, it's again 1. So both the functions take the value 1, and if we just take the difference, it's 1 minus 1, which is 0, it's vanishing. Similarly, for the lower values of n also, like n, whenever n is less than minus 3, let's say n equals to minus 4, in that case you will see that both the functions individually take the value 0. So 0 minus 0 is again 0. Only when n lies between minus 3 and 9, then the first function, which is u of n plus 3, it takes the value 1, right? And the second function, which is u of n minus 10, it takes the value 0. So the difference, overall difference, is 1 minus 0, which is 1. So I hope this is clear, right? Please ask me if you have any queries. So with this observation, actually we are expressing h of n here in a similar form to that of h of n minus k. So now you see the similarity. So this was given here, this was given here, this one, this was the given condition, and this we obtained based on our observation. Now now all we need to do is just do a time shift. Okay, once we have obtained this form of h of n, we can come up with the expression for h of n minus k. So it will be just the same thing. We need to replace n by n minus k, correct? So we have n replaced by n minus k, and what will be this condition here? The limits will be the same, just replace n by n minus k, and this is 0 elsewhere, correct? So what is this? If you just simplify this, we need to match with this given condition. So this bounds are on the parameter k, so we need to do that. So if we just modify this, rewrite this, we can also write it as k minus n lies between minus 9 and plus 3, or k lies between n minus 9 and n plus 3. Correct? Is it clear? So
Yes, sir.
good. So now just we can number these two equations, 1 and 2. We have exactly the same form here. So see, the form is exactly the same, half to the power n minus k minus 1, which is expected. And in equation 1, just the limits are different. The upper bound and the lower bound are in terms of a and b, and here we have in terms of n. So by comparing, one and 2, what can we say? Maybe I can zoom out a bit. Yeah. So based on 1 and 2 equations, what can we conclude? So we have come up with the upper bounds and the lower bounds for k in both the equations. We can simply match them, right? We can just equate them. So
Like a less than what is it? X k n.
huh,
Yes.
so this is the condition here,
Hmm.
okay,
Exactly.
and this is the condition here.
Yeah.
So these are the upper bound and lower bound for k we have obtained. So we can,
Yes.
if we just match them, if we just equate them, what can we write? What can we say about a? If we just
A equals to n minus 9.
yes,
A equals n minus 9 and b equals n plus 3. I can't see. Could you please zoom it, sir? Yeah, n plus 3. Yeah.
yeah. Can you see the screen?
Yes, sir.
Okay, exactly, very good. So this is exactly what we needed. So once we had expressed it in this desired form, we can, that's what was asked in the question. See, we needed to express a and b in terms of n, so such that this condition holds. So
Okay.
that we have done, like you said, it's exactly the same correct thing. So a and b we have expressed. So the first question is done. So
Okay.
we'll just move on to the, so this was very simple question.
Yes, sir.
So the second one, let's see. In the second question, we have been given an input x of n and the impulse response h of n. So they take the following form here. So and we need to find the output, which is given, as we know, by the convolution of the input and the impulse response. So let me just write it down. Okay, so our input is half raised to the power n minus 2 times u of n minus 2, and our impulse response is, by the way, please pardon me for my handwriting, it's really very poor, I know, but yeah. So yeah, and we need to find y of n, which is this. We will find this the mathematical form for y of n, and we will also plot it, see how it looks like. Okay, so yeah, Recording. Yeah, it's going on. Good. So, well, how do we do this? So, can you quickly give me the formula for y of n? Is the convolution of two discrete time sequences, x of n and h of n. Yes. What's the formula for the convolution? Discrete time. This is discrete time convolution. Remember?
Actually, it's been 8 years since I've touched this subject, so I won't.
Okay. I see.
Hmm.
All right. No issues. Yeah. So you can refer to the lecture notes or the videos anytime.
Sure, sir.
So for this discrete time case, this is given by x of k, h of n minus k, and k running from minus infinity to plus infinity. Okay.
Okay.
So
Now
how
I.
basically we do this is, so if I have to explain, step by step, then first we actually keep one signal as it is. Let's say x of n as it is, and but by the way, before, as you can see, a new parameter here which is k. So we introduce k here. So first step is basically to change variable from n to k. So we'll move from x of n to a x of k, and from h of n to h of k, and then what we do is, we keep one of the signal as it is. So keep, let's say, x of k unchanged, and we flip the other signal and flip h of k. So by flipping, I mean that we just reverse the time, do the time reversal operation. That is, h of k, we just replace k by k minus 1. Okay. And now what we do is, okay, I think we have run out of space. I'll add a page here. Then what we do is, we shift the flip signal by n samples. So we had h of n minus k, right? So we'll do a shift. So k goes to k minus n, and which is nothing but h of n minus k. So we already obtained previously x of k, and we kept it as it is, unchanged. So we have this x of k and h of n minus k, and the final thing to do is take their product and sum it over, do the summation over the entire range of k. Okay, so this is how we do the convolution for discrete time. In continuous time, as you can easily expect, this summation will be replaced by an integration, right? And we will have a dt term sitting there.
Yes, sir.
Yeah. So anyways, um, these are just theory things. So
Yeah.
for the given question here, I will write it down once again. So x of n is half to the power n minus 2 times u of n minus 2,
Minus h
and
of
h of n has been given to the u of n plus 2.
plus 2.
Good. So what we will do is, if we just follow the steps that I mentioned right now, so y of n again, as you know, is given by k running from minus infinity to plus infinity x of k times h of n minus k. So okay, so this h of so x of k will remain as it is. So x of k, if I see, x of k will be, we can directly write it here, x of k, just replace n by k, and for h of n again we replace n by k, then flip it and then shift it by n. So overall what we are doing basically is replacing n by n minus k, right? We are going from h of n to h of n minus k. So where is the, yeah, so h of n minus k is u of n minus k plus 2, correct? Now so both these forms involve the unit step function, right? The shifted unit step function. And what do you know about unit step function? It can take two values only. What are those two values? Can you recall? Like unit step function, if we have, say,
0 to 1.
Yes, either 0 or 1. So the definition is,
0.
so if we have u of n, so it can take the value 1 whenever n is greater than or equals to 0.
Yes.
And it is 0 whenever n is less than 0.
Yes.
And here this is a discrete time system, so we are talking about all integer values of n. All these indices are integers. So
Okay.
like n equals to -2, -1, 0, 1, 2, so on. In continuous time they can be any real number between minus infinity to plus infinity. Let's say 1.15, 3.2, that is also acceptable. But anyways, so this is the definition of unit step function. Now so if I just replace this x of k and h of n minus k, substitute it, so x of k is what? Half to the power k minus 2 u of k minus 2 times h of n minus k is what? U of n minus k plus 2. Okay, so far so good.
Yeah.
Okay, so now, so again, like we saw here, the unit step function can either be 1 or 0. So product of two unit step function, again there are only two possibilities. Whenever both are 1, the product is 1. If any one is 0, the product is 0.
0. Yeah.
True. So we are actually worried about this product here. Only depending on whenever this is non-zero, this product is non-zero, we will just take the summation. In rest of the cases, the product will just vanish, right? It will be 0.
Yes.
So u of n minus k, sorry, u of k minus 2, the first one here, when is it 1? Yeah?
When k is equals to 2, 3.
Correct. So k is greater
3.
than or equals to 2.
Yeah, okay.
So, and it is 0 elsewhere.
Okay.
I mean k is less than 2. So
Yes.
like 1, 0 and so on. So, and again similarly, this thing, the second one, it is 1 when k is less than or equals to n. Oops. Just a second. Okay, I wrote it. Okay, so it was n minus k plus 2, right? So n minus k plus 2.
Yeah, n minus k plus 2.
So this will be 1 whenever k is less than or equals to n plus 2. Why? Because we have u of n plus 2 minus k, right?
Yes.
So this thing has to be greater than or equals to k. for it to be 1. So in other words, k is less than or equals to n plus 2. So anyways, I just erase this. Okay, and it is indeed 0 as well. Now let's see how this graphically looks like. So if we take the first function u of k minus 1, if we just plot it as a function of k, so you see the threshold here is 2. From 2 onwards it takes the value 1. So for let's say index 0, 1, it is 0. From 2 onwards, k greater than or equals to 2, it takes the value 1. 2, 3, 4, 5 and so on. Yeah?
Yes, sir.
Okay, good. So and if we just plot the second function, which is u of n minus k plus 2, it is like this. So for k less than or equals to n plus 2, it is 1. Up to n plus 2 it is 1, and beyond n plus 2 it is 0. So let's say n plus 2 is somewhere here. So the previous index will be n plus 1, 1 less. This is n, this is n minus 1, this is n minus 2, so on. So up to n plus 2 it is 1.
Okay.
Yeah, and beyond n plus 2, let's say n plus 3 onwards, this is n plus 3, this is n plus 4, it is simply 0 by definition. So now if we just observe these two figures here, so this product here, u of k minus 2 times u of n minus k plus 2, so we saw that this product can be either 1 or 0. So this is 1 or 0. So when it will be 1, so see this the first sequence u of k minus 2, it goes to the right, it's a right sided sequence. So beyond 2 it takes the value 1, and this is a left sided sequence. Any value less than n plus 2 up to n plus 2 it is 1. So it's a left sided sequence, and this product of these two functions will be 1 whenever there will be some overlap between the two functions, correct? They will have some common value. Otherwise, if there is no overlap, it will be simply 0.
Okay.
So when is that overlap possible between these two functions? So if you see here in the first function, k starts from 2, and in the second function k is up to n plus 2. So
n plus 2, yes.
So what do you think, when will the product be 1, in which case? What should be, in which interval should k lie such that this product is 1, looking from this diagram?
When n plus 2.
So when so 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 I have drawn this figure in such a way that it looks like there is overlap, right? As if n here in the lower diagram is corresponding to, it's matching with 2 in the upward figure, and
Yeah.
so on. So this is the scenario when there will be overlap. I have drawn in such a way just to make you understand. So the thing is, the the upper limit, the maximum non-zero index for the lower function is n plus 2, right? Up to n plus 2 it is non-zero.
Yes.
So whenever, and the first non-zero value for the u of k minus 2, it starts from 2, right? K equals to 2 onwards.
Yes.
So whenever this n plus 2 here for the lower signal, that will cross that mark for the upward signal,
Okay.
so then only there will be overlap between the two,
Oh,
right?
yes, sir.
You get my point, right?
Yeah.
So if you just like visualize it for a continuous time signal also, had it been a continuous time signal like this, let's say, so it is 1 from some point t naught, okay, and another function we have, it is 1 up to a point, let's say t1 prime. So what will be the overlap? This is the overlap, this portion, right? This shaded portion, correct?
Yes.
So, and that this overlap exists only when t naught prime is greater than t naught. This limit is greater than this. True.
Okay.
So in this figure also, we want this n plus 2 to be greater than this 2 here. So this
Okay.
n plus 2 here to be greater than this 2. So
Yeah.
whenever n plus 2 is greater than 2. So yeah, so I mean yeah, so n plus 2 is greater than 2, that implies n is greater than 0. So this overall y of n, which involves this product, so this will be non-zero only when I mean it's greater than or equals to, so it just coincides. That's also possibility. So whenever n is greater than or equals to 0, we saw the product, it has some common overlap, right? And then only this summation will be actually having some non-zero entry, non-zero value. So our, which is our y of n, we are interested in y of n, finding y of n. So our y of n is non-zero only for n greater than or equals to 0. So this is why, because overlap, only when we saw n plus 2 is greater than this 2, that is n greater than or equals to 0, there will be overlap between them, and then only this overall y of n, which is the expressed as the sum over this product, this will be non-zero.
Okay.
So this is the thing, and which automatically implies that it is 0 whenever n is less than 0.
Okay.
So no need to write, but still it's 0 when n is less than 0. So but here, this product here, it will take the value 1 whenever our running index is k here. K is the index, so k will lie between this 2 and n plus 2 here. So 2 and n plus 2. Whenever k is between these two limits, then only there will be, they will have non-zero product, these two unit step functions.
Okay.
Right. So this is the thing, and it is 0 elsewhere. So okay, so just let me add one more page. Alright, so y of n equals so the form was like this. Again I am writing it, k minus 2 u of k minus 2 u of n minus k plus 2 okay. So we saw that this is non-zero when k is greater than or equals to 2, and this is non-zero, which is 1 when k is less than or equals to n plus 2. True. That's exactly what we wrote here in these two definitions here. This one, and this one, right?
Yeah.
Okay. So and okay, so only these two cases will give us this non-zero value for this unit step function. So their product will be 1 only when k is greater than or equals to 2, whereas k is less than or equals to 2. So this is the thing, right? Both this condition holds, then only this product will be 1, and in all other cases the product will just vanish. So our summation here, what we are doing is, instead of running from all minus infinity to plus infinity, we can reduce from 2 to n plus 2 here, right?
Yeah.
This will stay as it is. So what about this product? Only in this interval it becomes 1 times 1, which is 1. Both these functions take the value 1. True?
Okay.
So this is what k equals to 2 to n plus 2 half to the power k minus 2. Okay. Now if we just put in these values, okay, the first one is k equals to 2. What happens to our term inside summation? It is half to the power
0, right?
good, yes. And it will just keep on increasing.
Yes.
So till half to the power n plus 2 minus 2, which is n.
Okay. Yeah.
Yes.
Yeah.
So and what about this summation? This is very popularly known summation.
1 plus.
This is a geometric progression, right? GP series.
Yeah.
And how many terms are there, by the way, here?
1, 2, 3. 0, 1, 2. And so on to n. 3.
So the last term is half to the power n.
Yeah, half power n.
So total there are how many terms in this summation?
4. No.
No.
No. What could be the nth value?
So it will have n plus 1 terms.
Yeah.
So the first term is like raised to the power 0.
0. Yeah.
Second term is raised to the power 1. So there's a difference of a factor of 1,
N.
right?
Yeah.
So had it been 3 terms, it would have
Yeah.
ended in half to the power 2. So
Yes.
since it ends at half to the power n, so there are n plus 1 terms, obviously.
Okay.
Right? So
Yeah.
and the formula for this is given by, so this is a GP series with okay, let me write GP series with n plus 1 terms, and the starting value, the first term here is 1. So we take the first term and then we take the common ratio. So here the common ratio is half. So we are multiplying by half at every consecutive times, right? First we have
Okay.
0.
Yeah.
I mean, first we have 1, then we multiply by half, then again multiply by half, which is why it becomes half squared, and so on up to half
Yeah.
to the power n.
Okay.
So this common ratio to the power of number of terms, which is n plus 1 minus 1 by again the common ratio, which is half minus
N
1.
9.
So this is the
Okay.
formula. Okay, you can just revisit your
Yeah, sure.
mathematics for this GP series formula. So
Okay.
this is the thing, and if we just simplify this, we will get, so the denominator will become minus half, and if we just take it in the numerator, it becomes
Yes.
minus
1
2.
yeah.
So, and I'm just adjusting the signs here.
Okay.
Yeah, this is the expression. Okay, so, and
Okay.
remember that this is only true, this is the expression for y of n only when we saw that y of n is non-zero only for n greater than or equals to 0. Here
Okay.
I have written in this line.
Okay.
So this expression that we got here, when this is true when n is greater than or equals to 2. So, and otherwise y of n is what? It's 0, because of this condition here that we took. So the overlap between these two sequences will happen only if this limit is greater than this limit, right? These two will have some common overlap, like I showed with this diagram also. T naught prime, whenever T
Yes.
naught prime will be actually greater than or equals to, you should say here.
Hmm.
So that's why what we have used here. Based on this, we can determine that y of n is non-zero only when n is greater than or equals to 0, and it is 0 when n is less than 0. So we can write that y of n is two cases, right? This is the form it takes when n is greater than or equals to 0, and it is 0 when n is 0, n is less than 0. So do you see a similarity uh, of this y of n, I mean this interval of n, with some very known sequence? So it takes one form when n is greater than or equals to 0, and it is 0 for n less than 0. So can you come up with some function we have recently just viewed which has similar kind of characteristics, which is non-zero only for n greater than or equals to 0?
Is it impulse?
It's the unit step function
Unit step. Okay.
u of n. Here exactly what we have written. See this,
Yes. Yes.
this.
Okay.
So good. So since y of n is also following that thing, so remember u of n is 1 only when n is greater than or equals to 0, and it is 0 when n is less than 0.
Yeah.
So we can write y of n as this thing or not, half to the power this thing. If we just multiply this by u of n, isn't it the same thing?
Yes.
So whenever
Yeah.
we are multiplying by
Yeah.
u of n,
Multiply with u of n, it will be the same.
exactly, so it automatically becomes a right-sided sequence. It is only
Yeah.
only non-zero when it is positive, when it is greater than or equals to 0. So
Yes.
this is the actual answer for our y of n. Okay,
Okay.
so
Okay.
this is what this is the mathematical form. And now we have been also told to plot it. So we'll go to the next page. Okay, so y of n we just got 2 times 1 minus half to the power n plus 1 times u of n. Now what about the plot of y of n? Okay, let's take some sample values and then we check. So what about y of minus 1? What's the value of y of minus 1 if we put n equals to minus 1? Yes. Hello.
Zero?
Yes, 0. Yes.
Yeah.
Why 0? Because by
Yeah,
the
because nth and the power of n is minus 1, right? So
so why this y of minus 1 is 0? What's the reason?
why? Because n we have taken as minus 1, right?
Hmm. Hmm. So anyways, like so you're right. So if you put minus 1 here, so
Yeah.
this this product becomes 1, which you can like, write this. So this is minus 1 plus 1, which is 0. So 2 times this thing, so which is anyways 2 times 1 minus 1, which is 0. But
Yeah. Zero.
instead of substituting that, you can just observe that what about u of n. So u of n is only, so u of minus 1, if you do, it's 0, right? It's only, it takes non-zero values only from 0 onwards.
Yeah.
So you just don't need to check for the coefficient part which is present
Okay.
in front of u of n. So
Okay. Okay. Got your
since
point.
so that's the
Uh,
thing. So for remaining, for all negative values, it is automatically 0. You
okay.
don't
Okay.
even need to calculate this
For
first.
all the negative values, the unit step function is zero.
So which automatically makes this product 0, right?
Okay, sir. Got it.
Yeah, very good. So and if we put n equals to 0,
Okay.
in that case you can
In
check.
case. Hmm.
So this will be 0 plus 1, which is 1. And
One
what
minus.
is u of 0?
U of zero is great. Can be less than zero.
U of 0 is, going to the definition.
Hmm. And it is. It should be less than.
So this is the definition. What is u of 0 now? Tell me.
The n value should be less than zero.
No, I'm.
No. If n is equals to zero.
Hmm. What value does u of n take if n equals to 0?
Hmm.
Just look at this box, this definition. U of n is 1 whenever n is greater than or equals to 0.
U of n is 1. Okay. 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 So it is 1.
Yes. So u of 0 is 1.
1. Okay. So it is 2 into half. It's 1.
So we have u of 0 here, which is, okay, I'm
1.
writing it again for just
Yeah.
clarity. So this is half 2. So this is
It's
1 minus half, which is half, and
half.
this is 1.
1.
So
Which is equal
yeah, yeah,
to 1.
correct.
Yeah.
And what about y of 1 again? This is 1 plus 1, which is 2. And what about u of 1? What is u of 1? It's just 1. Whenever it's this parameter inside, whenever n is greater than or equals to 0, it just takes the value 1.
Okay.
So this is how u of n looks like. See, u of n as a function of n, if you see, for 0, these are the indices. So for n greater than or equals to 0, it is 1. It is 1. For all and so on, it continues. This is 1. And
You
For
N is
all negative values it is 0. It is 0.
okay.
This is how it looks like. This is the unit step
Okay.
sequence, unit step function or sequence. So what is u of 1? U of 1 is again this point here, right?
1.
This point,
Yeah, 1.
which is 1. Good. And what about this term sitting here? It is 1 minus 1/4 times
Mm,
1,
big by 2.
3 by 2. Good. 3 by 2. So 3 by 2 is 1.5.
Yeah.
Similarly, if you just calculate the some other values, so you will get y of 2 as 7 by 4, which is 1.75. You will get y of 3 as 15 by 8, which is 1.875, and so on. So the
Okay.
point here to note is that um, so if you just plot y of n, so we saw y of n. So all for all negative values of n, what was y of n? It was 0.
0.
Hmm.
Yeah.
So we are not bothered about all negative indices. Let's say any negative value, -3, -2, -1. Okay, this diagram is not at all accurate, but still. So these are all 0,
Yes.
and it continues for all lower values. For 0,
It is 1.
yes. So
And
I'm just
and
plotting it. Okay. So for
yeah,
0 we get 1.
1.
So let's say 1. This is 1. And for 1 we got 1.5.
Yes.
Oops. Something like this.
And then 1.75
Yes.
and so on.
And again like this.
Yeah,
So it keeps increasing,
exactly.
and it is, if you observe, it is approaching what value? It is approaching 2, getting
Yes.
closer and closer to 2,
Yes.
because you can also mathematically verify that, because
Yes, sir.
y of n is this thing, 1 minus half to the power
Minus
n plus 1 times u of n. So as n is increasing, n is tending to infinity more and more if you are increasing n. So
yeah.
for positive n, automatically this factor here is just u of n is just 1. So just keeping it aside, this
Okay.
term 2 times 1 minus half to the power n plus 2, what happens to this term? So as n tends to infinity, as n increases more and more, so what about this half to the power, this part half to the power n plus 2, what happens to this?
Exponentially increasing? No?
Yeah, but here you have to see this. See, this is actually what? This is half to the power n plus 1. So this is, I mean, 1 by 2 power n plus 1. So this factor here, let's say, when what
Okay.
happens to a power x, let's say.
Okay, okay.
So a power x, it can
I
exponentially increase depending on the value of a. So if
yes.
a is greater than 1, then obviously it will exponentially increase. If
Mm.
it is less than 1, which is the case here, it is half.
Okay.
So here this will tend to what? As n tends to infinity?
1 by
So 2 power n plus 1. And n is something very large, let's say. Let's say n is something like uh, let's say n is something like 1 0 0 0 0 0. So 2 power, you can imagine this value 0 0 0 0 1. This is in the denominator, so it's a very large quantity in the denominator, and we are taking the reciprocal of that.
Yes.
So what can we expect as the result? So something like this, 1 by 2 power 100 1 lakh, something like that. So
Po-
so this will approach what value?
um, m- Power minus.
Like this is a very large quantity in the denominator, right? 2 power
Yes.
this thing. Even
Yes.
if we have something like, let's say, 1 by 1000, so this is what, this is
Point
0.00,
1. Right. Mm.
right? So this is a
Mm.
very small quantity, right? This is
Yeah.
almost equal to 0.
Yeah.
So similarly here also, 2 power this 1 lakh is even a very greater quantity than 1000. So we are taking the reciprocal of that.
Exactly.
So this will approach
For
0 again, almost 0, right? This is almost 0.
almost 0.
Yeah. So as n tends to infinity, this what happens? This is 2 power infinity, let's say. Infinity plus 1 is again infinity, so infinity.
Infinity.
So this is tending to 0, right?
Okay.
So
Yeah.
1 by infinity, which is again 0.
This is- Yeah.
Okay.
Mm.
So I just directly write. So this tends to 0
Okay.
as n tends to infinity. So and what about, okay, I'll just erase this just for more space. Okay, so yeah, and we have this. What about 1 minus half to the power n plus 1? What does this quantity tends to as n tends to infinity? We saw half to the power n plus 1, it tends to 0. So what about 1 minus half to the power n plus 1? That goes to,
Mm. Even that tends to. If this is 0, then it is 1, right?
right, very good. That tends to 1 because this part tends to 0. So
But
1 minus 0 is 1.
yeah.
Okay, and again what we have is this factor of 2 sitting here in front. So this tends to
2.
2. Good. So you see why this kind of graph we are getting here. It is the values are getting closer and closer to 2, right?
Okay.
1.875. If you go just closer and closer to infinity, it will approach 2. Y of n will approach 2.
Okay.
So the thing is, as n tends to infinity, y of n tends to 2. So this is more or less a picture of the graph plot for y of n. And now, so I hope the problem is clear, right? The solution is okay.
Yes, sir.
Hmm. So just practice all these basic problems on convolution. With more and more practice, I think things would be clear. When is the overlap happening? When will be the summation actually contribute to the overall sum? We don't actually need to run k from minus infinity to infinity as in
Okay.
the generalized definition of convolution. We only need to sum it over the indices when the product is non-zero, whenever there is an overlap between the two sequences.
Okay.
So that's the thing. So for I think we are running a bit slow. So for the third problem is also based on convolution only. We have been given sequences x of n and h of n, and we need to find the convolution of this to find the output y of n.
Mm.
So I won't actually work it out because we don't have much time here. but you can follow the same kind of strategy to solve this kind of problems.
Okay, sir.
So anyways, I'll just maybe give a hint. So this is the third question, right? Third question. So it's always a good practice to draw the graph and visualize the signal, how it looks like.
Okay, sir.
So okay, so we have been given this information and we need to find the convolution. So again we just follow the same thing. In this case, actually it's a bit lengthy solution, I don't know what I should do, but anyways, you just follow the same steps like we did for the previous problem. First change the variable from n to k, so we get
Yeah.
x of k and h of k.
Okay.
Then we keep x of k as it is, we flip the sign of h of k from k to minus k,
Okay.
and then we just shift h of minus k by n samples, so we get h of n minus k, and we take the product of x of k and h of n minus k and sum it over all k. So that's what we do, what we need to do actually. And now for this problem, so you see this x of n would look like something like this. So it is 1 whenever n is lying between 3 and 8. Let's say 3, 4, 5, 6, 7, 8. And for all other values, it is 0. This is what we have drawn is x of n. This amplitude is 1, this height is 1. Okay, so this is what x of n looks like. And similarly, h of n will also look like kind of similar. So h of n is, by definition, it takes the value 1 whenever n lies between 4 and 15, right?
Yes, sir.
Okay. Okay, so 0, again just I'm writing the indices, 1, 2, 3, 4, 5, 6, 7. It's not, these diagrams are not accurate, just hand drawn, that's why. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on. So from 4 to 15, 4 it takes the value 1, 5 takes the value 1, so this is 1, this is h of n. And in all other cases, okay, this is, wait, and in all other cases it is 0, right?
Yes, sir.
Yeah. So what happens in this thing is that, so first step was basically we saw we replace the variable from n to k. So just simply if we do that, so we are just replacing n by k, right? And we keep x of k as it is, and we flip h of k. So this is what I am showing is a graphical approach of solving the problem. So what happens when we flip h of k? So h of minus k is what we need to visualize. How does it look like? So any guesses how can we plot h of minus k when h of k plot is given? Yeah.
Uh, we get minus values? No? Or
Mm,
no?
that is if we just multiply the signal itself with some negative factor, then we get negative values. That's a amplitude scaling thing. What you are saying is let's say minus 1 times h of k, which is minus of h of k.
Okay.
So in that case, instead of all these 1 values here, all these peaks, we will have minus 1. But the signal structure will remain the same. Between 4 to 15, h of this function will take the value minus 1, because the signal is multiplied with a factor of this uh, minus factor here. So this is just amplitude scaling, okay. So but what I am doing here is the time scaling. So this is the index k that I am multiplying with minus 1. So I am reversing the time, I am doing time reversal thing. And so the easy way to check, let's say for k, for h of minus k we want to plot the signal. So if you put x equals, if you put k equals to 0, what happens to h of minus k? It's still 0, right?
Yes.
Minus 0 is same as 0.
0.
So what is h of 0? Yeah, we already have the plot for h of k. So tell me what is the value of h of 0 from this plot?
0.
0. So for 0 it's fine. So let me take 0 somewhere here, okay, for this signal. So 0 for 0, k equals to 0, h of minus k is 0, we got just now.
Okay.
Okay, now what about k equals to 1, let's say. So for k equals to 1, h of minus k is what?
Mm, h of minus 1,
H of minus 1, which is what I have not drawn till here, so we can extend it,
which is again 0.
which is again 0, exactly. So and it continues, okay, it continues and so on.
Yes.
So which is again 0, like you said. So this is minus 1, so this is again 0. Similarly, k equals to 2 also, we will get h of minus k as h of minus 2, which is again 0.
0.
So it will go like this. For minus 3 also you can check. Okay, Oops, I'm sorry, just a second. Just a second. So for k equals to 0, we obtained h of minus k as 0.
Yeah.
For k equals to 1, we obtained h of minus k as 0 again. For k
Yes.
equals to 2 also we got the same thing.
Yeah.
For k equals to 3 we got the same thing. Like for k equals to 3 also you can check similarly.
Okay. Yeah, it will be 0.
It will be 0. So now what about, okay, so k of let's say what about k equals to minus 4? So if we take k equals to minus 4, what happens to h of minus k?
1.
Which is minus of minus 4, which is
1. H of
exactly
4, which
exactly
is 1.
exactly
Mm.
so h of 4 is 1.
Mm.
So this is minus 1, minus 2, minus 3, minus 4. So minus 4 will take the value 1. Okay, what about k equals to minus 5? What happens to h of minus k?
1.
Yes, which is h of basically 5, which is 1.
1.
So you
Yeah.
see the pattern here.
Hmm.
And for minus 6 also.
Similarly, like up till 15, yeah?
Exactly, very
So
good.
up to minus 15.
Up to minus 15, yes.
15 it will be the same. Yeah.
So I'm just writing like this, I'm not drawing for all the points. So up to
Yeah,
minus
I got it.
15 it will be
Yes.
1. So
Hmm.
you see, and for the remaining points from minus 16 onwards again it will vanish.
Yes.
Okay, so that's the thing. So you see what it actually gives is that,
Hmm.
so you can think of it as a, from h of k to h of minus k, it's like a reflection.
Yes.
It's like a reflection about the origin, let's say. It's just
Yes.
it was running from left to right, it's running from right to left here.
Yes.
So just the index will be flipped. So it was
Yes.
from 4 to 15, and this time it will be from minus 4 to minus 15.
Yes.
So good. So and now we when we just flip this, um, so h of minus, sorry, when we shift this by n samples, so
Hmm.
which is nothing but h of n minus k, what we do is, so all these places, all these indices, we just add n. So we'll have minus 15 plus n, so which is n minus 15. Similarly, so this basically this point is same as, it corresponds to this, and
Okay.
this is 1. So for n minus 16 it will be, when it will 0 and so on. And and this minus 4 will come somewhere here, so again that gets added by n, so it will become n
And
minus 4.
minus 4.
Correct. So again, like n minus 5.
5 and minus 6 and so on to n minus 15.
Exactly, so this is a time shift by n units. Okay,
Okay.
so and yeah, it continues. So this is how h of n minus k and x of k, they look like.
Okay.
Now by the way, what's the length of the sequences? So again, let me just draw it here. So this is x of k. We have drawn it before, and so all the remaining values are, by the way, 0. Okay, I'm not drawing.
Yes, sir.
On 9 also it is 0, and we just now got the graph for h of n minus k. So that has a similar pattern as that of our original function. It's just reflected and shifted, so flipped and shifted version of h of k. So we saw that it runs from n minus 15, so these are 1, so on it continues up to n minus 4. So, and all remaining values, they are 0. This is the same picture, this one and this one. So x of k has a length of so basically length of the sequence means the number of samples for which it is non-zero. So here you can see that for k equals to 3, 4, 5, 6, 7 and 8, it is 1, it is non-zero, and in the rest of the cases it is 0. So it's a sequence of length 6 basically.
Yes, sir.
And for this one, h of n minus k, its length is so it's from actually we had from 4 to 15, right?
4 to 15, yeah.
So
And
that's, I think
9.
no, 4 to 15. 4 to 15 is actually the difference is
No,
11.
no, yeah.
So but we have one more actually.
Yeah, 12, yeah.
Exactly. So the second one is a longer sequence than the first one. So when we do this thing now, when we write this formula, this thing, so we have x of k, we have h of n minus k. We what we do is we take pointwise product and sum it over all k. So that is basically as if we are sliding this window of h minus k, h of n minus k, this function, across this x of k, and we are computing the area under those overlapping region. So as
Okay.
if you get it right. So as if let's say we have something like this, and we have something like this, two functions, let's say we slide the second function from left to right. So at some point, if it is outside, if it's there no overlap, then the product will be 0, right?
Yes.
As and when it approaches the second function, the first, when there is overlap, so let's say like this, when we have an overlap like this, so this is kind of the common overlap, this is,
Yes.
so that product and the summation, the area under that, these two functions, that increases, and there will be a time when there will be a maximum overlap between the two signals, because this is moving from left to right, and
Yes.
at some point it will start to come out, right?
Mm.
And at one point it will just totally come out.
Yes, sir.
So for rectangular functions also, as you might have seen in continuous time, if we have two rectangular functions like this is in continuous time, some x of t, h of t, and if we just convolve these two, we get something like, and here I am assuming both are of the same width, so we get something like something similar to triangular wave.
Yeah.
as the output. But the logic is that again here also same thing we do the shifted and flipped version of one signal. We take that signal and slide over the another signal, and as we keep on sliding it, as the overlap increases more and more, this overall result, this thing increases. See, this y of t, it increases up to a certain point, right?
Yes, sir.
And as the overlap starts to cease, as it starts to decrease over time, y of t falls down gradually, and there is a time after which there is no longer any overlap and it goes to zero. So similarly here also we have just sequences instead of a continuous time signal. See, both these functions x of k and h of n minus k, they are discrete time functions, and both of them are taking the value 1. See, it's
Okay.
1, it's only 1 over a finite window, finite interval.
Yes.
So the continuous time analog you can imagine like this. So it's defined for all time from, let's say, 3 to 8, it takes 1 value,
Okay.
and for the another function it's like from 4 to 15, right? It was in our
It
problem,
takes one. Hmm.
it takes the value 1.
Hmm.
So again we are sliding, we are doing all this flipping the time and shifting it and then sliding it over another function.
Hmm.
So again we will expect something like this rectangular thing only.
Hmm.
So but since here I have drawn for the case when both have the same width, but in our problem actually both have different sizes, right? One is of length 6 and one is of length 12.
Then 12.
Okay.
Okay.
So the thing is there will be like 3 cases you have to consider. So I won't calculate it, but I'm just saying. So so these are the two functions, x of k and h of n minus k. We, let's say you are sliding h of n minus k across x of k, you are moving h of n minus k across x of k, okay, from left to right. So h of n minus k is a longer sequence, length 12 sequence. You are sliding a length 12 sequence across length 6 sequence. So there will be there will be some overlap after some time, when there will be some common overlap between the two signals. Yes.
Yes, sir.
So and that overlap will increase as we keep on sliding the second function with the across the first function.
Yeah. Hmm.
At some point the overlap will be maximum.
Yes.
So and it will continue to stay maximum in this case. So it's like initially we got this kind of a curve, right? This kind of an output, right? So it gets a maximum value and immediately falls down.
Yeah.
So this maximum value is corresponding to the case when there is maximum overlap between these two,
Yeah.
and they're exactly overlapping each other. So these widths are same, right? But in
Yes.
our case the widths are different.
Hmm.
So this is the situation. This is 4 to
Yes.
15 days. So this is the situation when the overlap starts to occur, okay.
Okay.
So this is the common overlap part, and so the first case is sliding, okay. So window sliding inside, I mean the overlap increases. So this is going from, let's say, left to right. So this is the first case, and the second case will be there will be the window will be completely inside.
Yes.
Which is the full overlap. So what I mean is something like this. So
Window sliding inside, completely inside. Okay, yes, sir.
and this is 4 to 15. So see this 3 to 8 function, it is completely okay, because its duration is how much? It's 6, and its length as we saw is 12. So this function is completely within this function, so there is full overlap, you see.
Okay. Yes,
So
sir.
this is the situation. So this is the situation 1, this is situation 2,
Yeah.
when this function completely gets inside the second sliding function, you see.
Yes, sir.
So similarly, the third case will be the event when window starts to come out, right? So basically the overlap is decreasing, so it will be kind of something like this. So till here something like this, 4 to 15, we still had maximum overlap. We still had this first function completely within the window of this second function, but once it goes something like this, once it goes beyond that point, let's say this is 4 and this is 15. So you see again, this in this case there is not, the overlap is decreasing, right? This is not full overlap.
Yes, sir.
Full overlap was case 2, this is case 3.
Yes. Yes.
By the way, this is, I am drawing continuous time signals here. Actually in
Okay.
reality it is like this, okay, this is, they are discrete samples, okay, like this and this.
Yes. Yes.
I hope that is understandable. I'm just
Yes,
drawing
sir.
for
Yes. Yes. I understood.
so so based on these three regions, our output, it will have three different cases and three different forms. So
Okay.
so you can expect that it will grow after a certain point, till certain point, as the overlap keeps and increasing as the window slides, right? And
Yes.
there will be a
Mm.
point of maximum overlap, and once
Mm.
that point is reached, which is case 2 here,
Mm.
this overlap will be constant,
Yes.
for that, right? The product, the area under those two things, it will be constant because both are of height 1 here. Just a second,
Yes.
where is the pointer? Yeah, so both are of height 1 here. So once it is completely, once the upper function is completely within the window of the second function, this
Mm.
overlap, this maximum overlap value, the area will be the same, okay, it will continue to remain the same.
Mm.
So this is like region 1,
Mm.
and this constant, so this is completely inside, this is region 2, this is the maximum overlap. And after, once that maximum overlap is exceeded and the window starts to come out, then output
It.
starts to fall
Mm.
down.
Yes.
So there will be three possible forms of y of n depending on these three cases.
Okay.
So what you will see is, so this is our actual output, this is our output. And if you just do a case by case analysis, again like the similar to question number 2, you have to choose the limits wisely. whenever that when is that overlap happening, for which interval, and calculate the sum accordingly. You will get different forms of y of n corresponding to these three cases. Okay,
Okay.
so what you can just verify that. So you can see that the final answer that you will get, check this. So what you will get is y of n will take the form n minus 6 whenever n lies between 7 to 12. It will be constant, that is the maximum overlap has been reached, full overlap. It will remain this, it will hold this value 6 for 13 to 18. It will be of the form 24 minus n from 19 to 23, and for all other cases it will be 0. So this is how it would take the form, and you can plot this function. You will observe that it kind of looks, you can easily plot that. I mean, this is nothing fancy. So what it will look like is, from n equals to 7 onwards, it will start taking values. So for 8 it's 2, for 9 it's 3, and so on. It keeps growing. Okay, it keeps growing, and at n equals to 12, at n equals to 12 it reaches the value 6, and
Okay.
from 12 to, it continues to stay in 6 for till 18, till 18 it stays on, let's say 18, it stays on 6, the maximum value, and from 19 onwards again symmetrically it falls down. So
Yes.
this is, let's say 5. For 11 we have 5. So for 19 we again have 5, and similarly it goes down, and for 23 we have 1, and for 24 onwards again it's just 0. So this is how y of n would look like. I have not drawn all the points. You can just easily draw it by plotting the values, and see the form. It's the same as this thing, right? It grows, stays constant, and comes to 0. Yeah, it's just the same thing. This is it's growing, it's holding at 6, the maximum value, and it's coming down to 0. So you can just plot it, and it's easy to verify this. So I'll quickly go through the remaining problems. So okay, so we have some more problems, but anyways let's continue. So fourth one is this question. X of n is given. It takes the value 1 whenever n lies between 0 to 9, and it is 0 otherwise, and h of n is from
0 to n.
0 to capital N. Yes, it is 1, and it is 0 elsewhere, and capital N is an integer which is less than or equals to 9. And we know that the output y of n is given by the convolution of x of n and h of n, and we need to find the value of n, and subjected to these conditions, y of 4 has been given as 5 and y of 14 is equals to 0. These two are the given values of the output for 4 and 14. So these are the information that has been provided, and we need to find capital N. So yeah, so for that I think it's good to start a new page. Okay, okay, 4. So again, let me just write it down. Okay, and we have been given, this is very important information, y of 4 is 5 and y of 14 is 0. We need to find capital N, and capital N has been given by, it's bounded by, upper bounded by 9, and it's an integer, of course. So, and what is y? Y is nothing but the convolution of x of n and h of n. So any guesses how to approach this problem?
Uh, it's the same method like before.
Uh, indeed, it's the same method because we are dealing with convolution, but here the thing is, one may think that okay, so it's like a from a linear algebra perspective, one may think that okay, so I have been given the value of the output for two values of n, for n equals to 4 and n equals to 14, I have been given
Mm.
what value it takes. Okay, if I can find the form of y of n first and
Mm.
then just substitute it, I get I can then find the value, the general uh, value of y of n, and then come up with the this capital N thing.
Mm.
So but for that you need to again explicitly find the convolution. The idea is not to do that, that will turn out to be a lengthy process. So um, the thing is
Nicole, is there any formula for n actually? 1 by uh, directly putting formula
directly putting formula for what?
to find out n.
To find out capital N.
Hmm.
So I mean, how do we do that? Like um, there's no such formula, I think, but I don't know. I mean, uh, what you are trying to say. In this case, I don't at least directly see any formula. You can try. You can try. Of course, any problem can be solved in multiple ways. There is not just one way of solving a particular problem.
Hmm.
There can be multiple approaches. So anything which is fine with you, you can do it. But the thing here is just, this is a kind of an observation based problem. So so I'll just, maybe first things first. So what is y of n? It's the convolution. So what's the formula?
X of k into h of n.
Right,
Okay.
this is the formula for discrete time convolution.
Hmm.
And we can further reduce it. This summation, instead of running from all minus infinity to infinity, entire this range, we see that x of n, it is 1 only when n lies between 0 to 9, correct?
Yeah.
And it is 0 otherwise. So
Hmm.
if you just replace n by k, so x of k will be again 1 whenever k lies between 0 to 9 and it is 0 elsewhere.
Yes.
So this first function here, x of k, it is non-zero. It is 1 only when k is 0 to 9. It is lying between 0 to 9. So we just do that. So if we just substitute the limits from 0 to 9, this coefficient here, x of k, it will be 1. And h of n minus k is there, of course. So, and in other cases, what happens to this summation? When k is outside this interval 0 to 9, what happens to this summation?
And
So,
0.
0, yeah, because
Yeah.
you see what's going on here. What I am trying to convey is you can write this, right? You can split this summation, right?
Yes. Yeah.
From minus infinity to,
To,
let's say, 0, or not 0, to minus 1. You can write x of k h of n minus k plus 0 to 9, k running from 0 to 9. In that
yes.
case we have x of k. Okay, let me again write it for you. Plus k equals to 10 to infinity. I can write it like this. I can write this entire summation from minus infinity to infinity into these three summations. I can express it, yes or no?
Yes, sir.
Yeah. So what happens to the first summation here? So the first summation here, whenever k is between minus infinity to minus 1, what happens to x of k? X of k is only non-zero. It is 1 only when k is between 0 to 9. So
Yes.
out of all these three summations that I have written, which one will be non-zero? Tell me.
The middle
Exactly,
one.
exactly. The middle one will be only remaining.
Yeah.
So k equals to 0 to 9. And what about x of k for that range? See here.
X of k range.
When k is running from 0 to 9, what about x of k? What value it takes?
Between 0 to 9.
Hmm.
The 1.
Yes. Times h of n minus k.
Yeah.
And this is again the third summation is again 0, which you just
0.
told
Yes.
me. Okay, so yeah, so this is the thing. So what we have is k running from 0 to 9 h of n
N
minus k.
minus k.
This is the thing. This is actually our y of n. We have reduced to.
Okay.
So um, so so this was our y of n. So y of n, if I just write it, expand this. So we have
Sherry?
we can expand it like this as k runs from 0 to 9.
Yeah.
And now the thing is, okay, so we already defined h of n. H of n was, okay, h of n was 1 whenever this this was the condition, and it's 0 elsewhere. So h of n, so this h of n is actually 0 whenever small n is greater than capital N. Up to capital N it's 1. If it's greater than capital
Hmm.
N, it's 0.
Okay.
And so what about h of n minus 1? That is 0 when you just replace n by n minus 1. Yes,
Yes, sir.
which is nothing but n is greater than cap n plus 1.
Mm.
Similarly, what is h of n minus, when is n, h of n minus 9 0? When when this thing is greater than capital N, which is n is greater
N
than,
plus 9.
correct. So you see this entire summation here. So whenever so okay, by the way, this is when n is greater than capital N plus 9, it automatically implies that small n is greater than capital N, because
Yeah.
capital N plus 9 is a larger quantity. So
Mm.
when small n is capital N plus 9, it is greater than this, then all this individual h of n, h of n minus 1, all of them vanish up to h of n minus 9. So the overall sum is 0. So the first term will vanish when small n is greater than capital N. Second term will vanish when small n is greater than capital N plus 1. Similarly, the last term will vanish when small n is greater than capital N plus 9. So, and small n being greater than capital N plus 9 automatically takes care of the remaining cases, right?
Yes, sir.
Right, because capital N plus 9 is the larger number. So what
Yes,
I
sir.
am saying, like n greater than 11, it automatically implies that n greater than 2.
Yes.
So like that. So the overall function y of n, it will be 0 when small n is greater than capital N plus 9. Now we have been given that y of 14 is 0.
Yes. And via 4 also. Yeah.
I'm coming to that, but
Mm.
so y of 14 is 0. So
Yeah.
we just now discovered that y of n is 0 when small n is
Yes.
greater than capital N plus 9. So
Yes.
for n equals to small n equals to 14, this condition must hold because it is 0.
Yeah.
So that implies this small n, what is this small n here? 14. 14 should be greater than cap n plus 9.
Yes. Yes, sir.
Yes, and so what we get is n is less than 5. So n strictly less than 5, that means n is
Yeah. N
less
is
than or equals to 4.
yeah.
This is
Okay.
one condition. Okay, this is one condition that we have gone. Let's say we are leveling this by equation 1. So now, so capital N, we need to find the value of capital N, but we have derived an upper bound on capital N, which is fine. So now the thing is, okay, so
Yes, sir.
now we have been given that what you are saying is, okay, let me go to the next page. So we have been given y of 4 equals to 5.
Hmm.
Now observe carefully that so basically y of n is the convolution of x of n with h of n, and it is taking the value 5 at n equals to 4. Fine. So and individually x of n and y of n, they are uh, they are just constant functions, so they are taking the value 1 in a finite interval. X of n is 1 when n lies between 0 to 9, and h of n is also taking the value 1 when n lies between 0 to capital N. In all other cases they are 0. Okay,
Yes.
So they're kind of like these kind of functions. Within some interval they are 0, they are 1, and for other cases they are 0. I'm just drawing a rough diagram. So yeah, like this. So, and since their amplitude is 1, and convolution involves, as we saw, sliding of one function across the other function, taking their pointwise product and summing it up, right?
Yeah.
So whenever there will be overlap, what will be the product of these two? Like the pointwise product, it will be like whenever they are matching, it can be maximum up to 1 times 1. Each can
Yeah.
take 1 maximum value.
Yes, sir.
Okay, so it has been, and now by the way, like length of x of n is how much? X of n, we saw that it's 1 only within 0 to 9. So 0 to 9, n equals to 0 to 9 encompasses how many points? 10 points. From 0 to 9 we have 10 points. So 10, for 10 indices it is 1, it is non-zero. That's why the length of x of n is 10.
Yes.
And length of h of n,
Okay.
since h of n, if you just recall, it was defined like this,
Yes.
and it is 0 otherwise.
There. Yeah.
So its length will be capital N plus 1. From 0 to capital N there are capital N plus 1 indices.
Yes.
This is capital N plus 1, and it was already given that capital,
N
sorry,
is
less than 9, it was
9.
given.
Yeah, it was less than 9.
So capital N plus 1 is less than or equals to 10.
So, but we got n is less than or equal to 4, right?
Yeah. So but
Mm.
but that's yeah, that's what we got. That is a even more tighter bound that we got. So but this is also true, right?
Then which value will be considering, like 9 or 4?
No, we haven't yet find the exact value of n, right? This is just a bound that we have got. So
Okay.
n, till now n can be anything. N can be 1 also, because
Okay.
1 is less than or equals to 4. 1 is also less than or equals to 9. Right?
Okay.
We still haven't solved the problem yet.
Okay.
So so yeah, so this n plus 1, this length is less than or equals to 10. So what I am trying to say is this h
Mm.
of n is either shorter than or equal to x of n
Okay.
in length.
Okay.
Right, we just mathematically verified it.
Okay.
So now, so let's say this is h of n, this is x of n. So and we are sliding h of n across x of n. So we have been given y of 4 equals to 5, y of 4 equals to 5. So that implies there must be at least 5 non-zero overlaps between these two signals, because individually they are taking the value 1. Okay, pointwise product is 1 times 1, which is 1.
Okay.
So there must be at least 5 such products, right? Pointwise products, because you can write 5 as 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1 plus again 1 times 1. So there must be at least 5 such overlaps, correct?
Yes.
When
Yes.
both the functions are taking the value 1. You get my
Okay.
point, right? And you are just doing this pointwise multiplication and adding it, which is just the
Yes.
convolution.
Okay.
You get my point.
Yes, sir.
So there must be, the observation is this implies that there must be at least 5 non-zero overlap between x of n and h of n. Then only we can at least get the value 5 as the result, right?
Yes.
Yeah, which is obvious. So the thing is, and out of x of n and h of n, h of n is the one which can be the shorter length sequence, right? We just saw here, we just wrote it here. Since
Yes.
n plus 1 in length is less than or equals to 10, so it can be the shorter sequence.
Yeah.
So for that reason, the shorter length sequence must be at least of length 5. Then
Okay.
only the product will continue till 5 cases, right? Five indices, right?
Yes, sir.
So the thing is, um, I mean, therefore, length of the smaller one, which is h of n, must be at least equals to 5. Then
Yes,
only
sir.
we will have 5 pointwise multiplications,
Yes.
and that will result in 5. And what is the length of h of n? It is this cap n plus 1 we have written.
Capital N plus 1 less than or equal.
Capital N plus 1 is the length of the sequence. So capital
Okay.
N plus 1. This is length of h of n.
Okay.
That must be greater than or equals to 5.
Okay.
So what do we get? N is greater than or equals to?
4.
Correct. So let me label this as equation 2. Now tell me, in equation 1 we got this condition.
Yeah.
N is less than or equals to 4.
Yeah.
And we just now saw in equation 2 n is greater than or equals to 4. So by comparing these two equations, what can you conclude?
It lies between. Okay. Great.
I'm writing the equations once again for you. Equation 1 was this.
Yes.
Equation 2 is this.
Yes.
Now what's the conclusion from these two equations? So in what condition these two equations are valid? Tell me. When are these two conditions satisfied simultaneously? First one is an upper bound, it's an maximum value which we are getting. The second one is the minimum value that we are getting. So this variable n,
Yeah.
so it has a maximum value of 4, and
4.
it also has a minimum value of 4.
Yeah, it lies between both plus.
So I mean,
Maximum and minimum.
so I mean,
Uh,
is when is it possible? Like one function is less than or equals to some value, and it is also greater than or equals to that same value. When is that case possible? This is like,
oh.
so from 1 and 2 we have n exactly equal to 4.
Okay.
See, then only these two equations are satisfied, right?
Okay.
4 is less than or equals to 4. True. Any number is less than or equals to that number itself. Also, 4 is greater than or equals to 4. That is also true. Any number is greater than or equals to. This inequality is true. So, only possibility for n is this 4 exactly equal to 4. Then only this equation 1 and 2 are satisfied.
Yes, sir. Okay.
You see the thing. So, I mean, graphically, if you observe,
Yes.
So first one is saying capital N is less than or equals to 4. So let's say this, I mean this is the range, it has to be less than or equals to 4. This is equation 1. The second one, what does it say? It says 0 1, sorry, this is 2 3 4. Second one is saying n has to be greater than or equals to 4. So from 4 onwards, like this, these are the acceptable values of n, capital N. So tell me, when are these two simultaneously holding true, this 1 and 2 from the diagram?
Yes, when it is equals to 4.
Exactly, only for this point, right? Only for
Yes.
this n equals to 4 point. So that's exactly what we are getting, a single point, a single value of capital N, which is 4. It satisfies both the conditions. So that's exactly what we needed to find, the value of capital N. So we have done that, and this remaining problems, okay. So I mean there are many problems, but let me just okay, let's say we discuss one or two parts of this, okay. So question number 5 says y of n is given by this. It's summation over k running from minus infinity to plus infinity x of k times g of n minus 2k, where g of n is defined by this. So it's the difference between u of n and u of n minus 4, and input is x of n, output is y of n. We need to take care of these 4 cases. So first determine the output y of n when input is delta of n minus 1, is the shifted impulse, right?
Yes.
Let's write it down. By the way, let me just check if the recording is going on. Yeah. So okay, so 5, in 5 we have this thing, and g of n is defined by this. Okay, so first part asks us when x of n, the input is delta of n minus 1, then what is our output? Okay, yes.
Yes, sir.
Okay, so what do we get here? Y of n is so we just put it here, x of k times, so what is x of k? So x of k is, x of n is given delta of n minus 1, so what is x of k?
X of n is given
As delta of n minus 1, so what is x of k? So
k minus 1. No.
x of n is delta of n minus 1.
X of k is delta of k minus 1.
Exactly, so just replace n by k.
Yeah, n by k. Delta of k minus 1.
So I'm just doing that, and so delta of k minus 1 times g of n minus 2k as it is.
Same, yeah.
So now, okay, now tell me, what about this summation? Okay, let me go to the next page. So we got y of n as summation k equals to minus infinity to plus infinity delta of k minus 1 times g of n minus 2k. So what is this summation equal to? Any guess? This is very simple, very easy. Just recall the definition of unit impulse function.
Yeah, that is what I was about to. It is an impulse function.
Yes.
But mm,
So this,
delta of
yes, go on.
k equal to minus delta of n equal to y of n minus k. I don't remember.
Okay, no problem. Just recall your notes. So
Yeah.
the definition of this discrete time data function is that this delta of
Delta
n
n.
is 1 only when n equals to 0,
Okay.
and it is 0 for all other non-zero n. Okay, so
Okay.
it's like this. That's why it's called an impulse. So this is takes the value 1 only for n equals to 0, and for minus 1, minus 2, and so on it's 0. For 1, 2 it's also 0. So this is delta of n. Okay, only for n equals to 0 it is 1.
Hmm.
So we have a delta of k minus 1 instead of delta of n. So that again follows the same definition. It is 1 when this parameter inside k minus 1 that is equal to 1, that is equals to 0.
Hmm.
This is 1 when k minus 1 equals to 1. Previously we just had n as the parameter. Here we have k minus 1.
Okay.
Okay,
Hmm.
which is same as k equals to 1,
Yes.
and it is 0 otherwise.
Yes.
So we know this. So this is 1 when k equals to 1, and this is 0 when k is not equals to 1 in all other cases. Now just look at this summation here. From this definition here, you can just use this definition here in this summation.
Okay.
What will you get? Tell me.
1. Uh. Yeah. When k is equals to 1.
Yes. Only
1.
that term will survive, right?
Yeah.
So from instead of running from entire minus infinity to infinity, you just
Yes. Hmm.
take the value when k equals to 1.
When k equals to 1.
Yeah, so our y of n will be only because why? Because in all the other cases when k is not equals to 1, this delta
Yeah.
function is 0,
0. Yes.
and this summation has no contribution, right?
No. Yes, sir.
So it is delta of k minus 1 at k equals to 1, it is 1
1.
times g of
The remaining y of that is g. Okay. G of n
this is
minus
g,
2k.
yes.
Okay.
Y is on the left hand side, which is the
Yeah.
output,
Okay.
and this is g.
Okay.
So and g has been defined as this thing in the question. Where is it? Yeah, this u of n minus u of n minus 4.
Minus 4. Okay.
So this is the thing, and yeah, so exactly, so we are
Now,
almost done.
we can substitute this there. Okay. Okay.
Yeah, exactly. So okay, so just a second. mm. Okay, by the way, yeah, okay, so we just missed out one thing. So this summation, it is only consisting of only one term corresponding to k equals to 1, right?
Yeah.
So this is basically this this second term evaluated at k equals to 1, only
Yes,
that is
yes, yes,
surviving, correct?
yes, correct.
So this is nothing but g of n minus k equals to 1. If we put, this is g of n minus 2.
Hmm.
So, and we have been given that
G of n is equals to u of n minus 1. If g of n minus 2 is equals to u of n minus 2.
so what is y of n? It's shift of g of n by 2 samples.
Yeah,
So, and we know g of n is this difference
yeah.
between u of n and u of n minus 4. So tell me what is y of n now. You just shift this by 2 samples, what you get in terms of this u function.
U of n my 1 second. Y of n is equals to g of n minus 2.
Hmm.
Wait, y of n.
G of n is known to you.
Yeah.
This one, u of n minus e of n minus 4. You need g of n minus 2.
U of n minus 2. No. U of n minus 2
Hmm.
minus
Minus
u of
u of
n minus 2 minus 4, which is
exactly
n minus 6.
exactly. You just replace n by n minus 2.
Yeah.
Exactly. So this is your actual answer. So
Okay.
this is for the first part we have done.
Okay.
When input was delta of n minus 1.
Okay.
Now coming to the second part. In the second part we have been asked about the output when x of n is delta of n minus 2. Previously it was n minus 1.
Yeah.
So now x of n is delta of n minus 2. So again is the similar process only.
Yes, just we can change the values above there
Exactly.
and
So
uh,
but let me just write this. So what you were saying, by the way, change the value, what you were saying?
like before we had n minus 2.
1.
Mm, like we have to find y of n when n value was it was n minus 2.
Hmm. Hmm.
Could you please show me the question once?
Yes, sure.
Yeah. First one is like determine y of n when x of n was delta of n minus 1.
Yes.
And the next one is like delta of n minus 2.
Yes.
So the steps are same, just we need to do small calculations
Hmm.
in the above problem.
Exactly. Exactly. The method is the same.
Method is the same. Yeah.
Yeah. So let's just quickly do that.
Yeah.
I no need to explain it once again.
Yeah.
So this is now what this is k running from this to this. What is x of k? It is this time delta of k minus 2.
2. Yeah. H of
Oh,
n minus
by the way,
k.
this is not this is not h here. It was g, right, in our problem. In our
Yeah.
problem, the symbol was g.
Okay.
And it was g minus 2k, I think. Let me just go to the problem. G minus 2k. So g minus 2k. Okay, and this in this case again only one term will survive. So
Hmm. The
this will be
same.
1 when will it will be 1, this delta function delta of k minus 2.
When k is uh, around what k minus 2 will be 1.
K minus 2 will be 0. When the
Yeah,
parameter inside is 0, the value of the delta function is 1.
yeah, 1. So
So
2,
yes, yes. So this is 1 when k equals to 2,
2.
and this is 0 in all other cases. So, and this summation will have only one term which is corresponding to this k equals to 2.
Hmm.
So, so the first term delta of k minus 2 becomes 1 for
1,
k equals to 2,
2,
and the second term
and
is n minus
minus 2k.
2 into 2, which is 2 into
4
2, so g of n minus 4,
minus 4.
and g of n was u of n minus u of n minus 4, and similarly we we can just shift it by 4 units here.
Yeah.
So
So n minus
so
8.
so it
Okay.
will be u of n minus 4 minus u of n,
Hmm.
since g of n has been given to be u of n minus u of n minus 4, it has been given in our question, so we just replace n by n minus 4
Yeah.
and we get this.
Hmm.
Now, okay, in the third part it has been asked whether this system S governed by this input output relationship is this LTI system. It has been already mentioned that it is a linear system. Now we need to check whether it is LTI, whether it is linear time invariant system or not.
Okay.
So whether it is time invariant or not, we need to check.
Okay.
That is the third part. So is S, okay, is system LTI? Since it is already given to be linear in the question, we just need to check whether it is time invariant or not.
Okay.
So yeah, I mean, the hint to this is, first of all, let me ask you, what is time invariance?
Varying from minus infinity to, which varies with time, right? The signal that varies with time.
That is time variant.
Yeah.
And what is time invariant? That which does not vary with time.
Where, yeah, it does not varies with time.
But actually, if you just go through the notes, and this is actually same as shift invariance, both are used interchangeably, they are the same thing.
Okay.
So just recall, you just brush up your notes.
Sure. Sir. I
And
actually directly like I've just today only logged into this course.
oh, okay, okay, I see,
That
I
is the
see.
problem. Actually, I've registered and today only I've opened. So I found this and I clicked on the link.
Oh, I see, I see, I see, I see. Okay,
Yeah,
okay,
that.
okay. Then it will be difficult, I know, I understand.
Yeah.
So
I
because
haven't gone through the before weeks
okay, okay,
videos also.
okay.
I'm just directly logging into your lecture now.
I see, I see. Actually, yeah,
Yeah.
that's why it's taking a bit
Lot of
more
time.
time for every step.
Yeah,
I
it's like
understand that.
you're really being patient with me
No, no,
and
like
giving me
it's,
all the
yeah, it's my job, but
you
it's also helping me because this way I am able to interact with you also, which is
yeah.
actually how this session is supposed to be. Usually,
Okay.
people don't tend to respond or anything in the class, so I am not able to even detect whether students are present or not. So, but this is good.
Okay.
But
Yeah.
okay, because this is the third week's content, so of course there are week
Yeah.
one and week two. So just go through them in your free time once.
Sure, sure. I have
Then,
to actually.
ha 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 ha.
In like at present I'm working in a school, but I want to go back to my engineering college. For I was an assistant professor for 1.5 year.
Okay, 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 okay.
So now I'm planning to go back. So I just wanted to, before I go back, I just want to brush my
I
basic knowledge
see.
and
I see.
everything.
I see. I see. I see. I see. Okay.
So I've registered for the course and I wanted to start now. So when I've seen that it is there like today's session, so I just logged in.
Okay. Okay. No. No worries. It's fine.
Yeah.
So, yeah. Okay. Anyway, so in that case,
Mm.
okay. What is time invariance or shift invariance in other words?
Yeah. Yeah.
So, the definition is like, in simple terms, if we have an input x of n to a system and we get a corresponding output as y of n.
Y of n. Yes, sir.
Okay.
Mm.
If to this system we feed an input that is delayed by some amount n naught, okay, n minus
Okay.
n naught.
Okay.
If our output also gets delayed by the same amount,
Okay.
in this case our system is said to be time invariant.
Okay.
Time invariant means it is
Getting the same output.
not getting the same output, but shifting the input by an amount results in the output also getting shifted by the same amount.
Okay.
So here you see you are shifting the input by n naught, the output also is getting shifted by
Shifted
exactly
by
n
the
naught.
and not. Yeah.
So then the system is time invariant or
Okay.
shift invariant. Okay,
Okay.
that's why shift
Okay.
invariant. So
Okay.
shift, so basically time or shift invariant system. So
So if we see our problems, yes, they are shift invariant, right?
is it?
Bec-
Is it?
yeah, they are.
Okay, let's see. Let's see.
No,
Uh,
not 1 second. Let me check because what we got. Hmm.
this was the point to actually go through the part A and B so that we are able
Hmm.
to solve the C part.
It is getting shifted actually, but because that was what they said, delta n minus one and delta n minus two. Can we? Ayo, I think yeah, I didn't write, but
Okay,
yeah.
let me just write it down. Okay,
Hmm.
so now that you get by the way, and
Yeah, yeah, yeah.
if
You can just scroll up, no problem.
yeah, no, what I was saying is if this condition is not satisfied, then it's called a time variant system. Okay,
Yes, yes,
the
yes. I got your
counterpart
point.
or the
Yeah.
shift variant system. So okay, so
See, we got here, right? It was delta n minus 2, and we got something like of.
hmm
There is a shift in the time. N minus
yes,
2 we were giving, and we got n minus 4, and so on, n minus 8.
correct,
So there is a shift in the time.
correct.
Yeah, then I think so. This is shift LTI, isn't it?
Um,
No?
wait. I think you are getting a bit confused. So this is what is our thing? We need to check whether delaying the input or shifting the input by some amount results in the output also getting shifted by the same amount or not. That
Okay,
is what we need to
same.
check.
Okay.
Okay, so
Mhm.
just to be sure. Okay, so in part A we saw that if oops, if x of n is delta of n minus 1
Mhm.
and we feed it to our system, the output that we got was, let me just go to that part.
Yeah.
So this was delta of n minus 1, and output we got
We
was
got was,
this g
yeah,
of n minus 2, right?
yes, g of n min. Where did it? Oh yeah, g of n minus 2.
We can further actually express it in terms of u function, which will be
Hmm.
like two terms. No need.
Yes.
It's g
Okay.
of n minus 2, right?
Okay.
So g of n minus 2. Just to make it more compact. So this is y of n we got was g of n minus 2.
Okay.
In part B, our input was delta of n minus 2,
N
right?
minus 2. Yeah.
That we are feeding to our system. And by the way, we are denoting the system by S as per the notation used in question. So the system is S. And
Yes.
what output did we get in the second case in part B? Let us see. Oops.
N minus 4.
Correct, correct. So for delta of n minus 2, we got g of n
G
minus
of n
4.
minus 4.
Okay, great. So we got, okay, fine. So now tell me, from our definition here of time invariance or shift invariance,
Yeah.
is this system time invariant or not? Now tell me.
It is varying in time.
Yes, it is varying in time.
Yeah. And also it is getting shifted.
Yes, it is getting shifted. But what we need to see this is that the shift occurring at the input at the output, are they by the exact amount or not?
No, they are not.
Why not?
We, we are giving delta n minus 1
Correct.
and we are getting gn minus 2.
Okay, that's the first case.
The time is not same.
Okay, I mean, see, this thing is, um, the
You
point.
told that whatever
Mm-hmm.
time should be invariant, right?
Yeah, I mean, see, from this diagram here, from this definition here,
Hmm.
previously the input was x of n.
Yeah.
In the
We got
second
what?
case, in the second case, we are applying x of n minus n naught.
Hmm.
So this is input shifted by
N naught.
n naught, exactly.
Hmm.
And previously the output was y of n. In the second case, the output was y of n
Was,
minus n naught.
yeah. Hmm.
So this is output also shifted by
N naught.
n naught. Good. Now coming to this case. So
Yeah.
previously it was delta of n minus 1.
Oh.
In the
Shifted by
second,
1. N
correct,
shifted by
correct,
1. But
correct.
by but here when the output came, it is a
It
unit
it is
more.
exactly, exactly.
Uh,
So the output is shifted by actually 2,
2. Yeah. Output is shifted by 2.
by 2. Oops. Right, from because from g of n minus 2 to g of n
2.
minus 4,
Yeah.
there is two
Yeah.
shifts.
2.
So now from just from this definition, previously this in time invariant systems, this shift is constant. It's the
Okay.
same for input and output for
Hmm.
the two cases. So now here we saw that if we just shift the input by one sample, then
Hmm.
we are getting an output which is shifted by two samples.
Yes.
So the shift is getting varied, right?
Yes, sir. It is getting varied.
So this is a shift variant system.
Okay.
It is not shift
Invariant.
invariant. So this is not, oops,
Not shift L T
Exactly.
R.
Okay, I think it's not. Okay, just a second. This is a shift variant system.
Variant system. Yes,
Hmm.
it is getting varied.
Exactly. This is not
Hmm.
shift invariant system.
Yes.
And shift variant, this is same as time variant. So the time, these terminologies are the same. Okay.
Okay.
So not time invariant system. So this is not LTI system. By the way, LTI stands for linear time invariant.
Invariant system. Yes.
Hmm. So it was linear, it was already mentioned in the question.
Yeah.
This is a linear system. Is. We just
Okay.
needed to check whether it was time invariant or not. And we
Okay.
concluded that it is not time invariant.
Yeah.
Correct?
Yeah.
Okay. And similarly, we can also do the part D also. We have already run out of time. So
Okay.
so
Yeah.
for this, anyways, I think like it will be everything will be new to you. Even if I
Yeah.
just walk through the 6 and 7 problems,
Yes, sir.
it will be difficult for you to understand all the things at one go. So
Yes, sir.
just I suggest you just go through the notes in your free time or the videos,
Yes,
and
sir.
once you cover the contents, then we will be in the same page, and you will be able to understand everything very well easily.
Yes, sir.
So
Mm.
anyways, we have also exceeded the time. Actually, I am supposed to conduct this session for 2 hours. So already I have exceeded that. Oh, it's almost like 2.5, beyond 2.5 hours. So
Yes, sir.
anyways, I will maybe stop here at this point.
Okay, sir.
So, and I think all of you will get these recordings and the contents, these questions and all, in some Excel sheet. So that will be supplied to you. So in your free time later on, you can work them out. Uh, okay. So yeah. So I think it's fine. I'll just stop the recording at this point.
Thank you.